The chain rule provides us a way to find the derivative of composite functions. A composite function would be a function composite is another way to say nested functions. So for instance, that's a quadratic polynomial function, and then I'm going to take it to the 8th power. So I'm really doing two separate things here. I'm evaluating this quadratic, we could call that the inside function, followed by another function raising something to the 8th power. Some other examples would be e raised to the sine of x. So we're going to start with sine of x, that's our inside function, or the innermost function, and then we're going to follow that by doing an exponential. Okay, maybe you're starting to see the idea. Right, but it's one function applied after another. Right. So in this way, another way to think about composite functions is they're a two or multi-stage process, two or more stage process. Right, we start with a number x, right, and we apply some result to that. Okay, some function to that, and get a new number. Let's call it u. Right, I might call this first function g. Right, so we have u is equal to g of x. In our first example up above, our inner function is u equals x squared plus 3x plus 10. Right, and then we're going to apply a new function to our new number u. We could call it f to produce a result y. So y equals f of u. In our first example there at the top of the page, we've got y is equal to u to the 8th power. Right. So it's a chain of functions, one function after another. And to take its derivative, I need a chain of derivatives, which I'm going to multiply together. That's what the chain rule says. All right, let's read what the chain rule says, and then we'll spend some slides trying to get the idea. Here's what the chain rule might look like in a typical textbook. Okay, this first part here says if g is differentiable and f is differentiable at the right spot, then the composite function, right, our nested function, is also differentiable. Right, we'll pay a little bit more attention to what those ideas of differentiable mean in a minute. The derivative of the composite function, right, is going to be given by this rule. I need to take the derivative of f. Now remember, f is the last function we apply, multiplied by the derivative of g. Right, we could read this as it's the derivative of f evaluated at g of x times the derivative of g of x. Okay. This will make more sense as we go forward here. We're just kind of getting the statement of the theorem. But the main thing to note here is that the derivative of a composite function is a product of the derivatives of the pieces. We can also write this in what's called Leibniz notation. When we write primes, that's called Newton notation. When we use dy dx, all right, or d over dx, that's called the Leibniz notation. Right. So if we have this chain of functions, again we have, here's x, and it's getting sent to u by g, and lastly that's getting sent to y by f. Okay. Then the derivative of y with respect to x is the product of the derivatives. It's dy du, so I need to find this f prime of u, times du dx. So each link in the chain is going to have its own derivative, and I have to take the product of those links in order to get the derivative of the entire function. Why do I need the product? Well, one way to think of it is in terms of rates of change. Okay. The idea here is, let's suppose that we have one of these composite functions. Okay. Let's suppose y is changing at a rate 5 times faster than u. Right, and u changes at a rate that's three times faster than x. Okay? Now if I take these together, y is changing 5 times faster than u, which is changing 3 times faster than x. All together, y changes at rate, I have to take the product of the rates. 3 times 5, which is 15 times faster than x. Right. So for every unit change in x, I get 3 changes in u. And for each change in u, I get 5 changes in y. Right. So for 1 goes to 3, those 3 get multiplied by 5 to give 15. That's the chain rule. All right, let's see it in terms of symbols here. All right, we've got our composite function here. We could also write it as f of x is f of g of x. So first we apply g to x, and we take that result and plug it back into little f, and that's how we finally get our result y. All right, let's stick with the idea of rates, but now we're going to write it symbolically. All right, how much faster, what is the rate of change of u with respect to x? All right, we call that du dx, or g prime of x. Right. So this is the rate of change of u with respect to x. All right. And then y, the rate of change of y with respect to u is dy du, or f prime of u. And that's the rate of change of y with respect to u. So if I'm going to take the product of those, I get the entire rate of change, dy dx, is equal to, I'm going to start on this side just to be consistent with the way that it was written in the beginning, times du dx. If I write this in Newton notation, y prime, or f prime of x, big F now, is dy du. That's f prime of u times g prime of x, du dx. But remember here, u is shorthand for g of x. Okay, so if I substitute that into u equals g of x into my result here, we get y prime, or f prime of x, equals f prime of g of x times g prime of x. I'm sure it's still confusing, but the idea here is if we're going to compose functions together and we want the rate of change of the composition, we have to take the products of the rates of change. Okay? We'll see how to simplify the mechanics here in just a bit. Okay, so let's look at the idea in the context of this example. I have a composite function here. Right. The inside function is what we do first to x. So we evaluate that quadratic, followed by the outside function, which is to take u to the 8th power. If I want the derivative of y with respect to x, okay, in Leibniz notation, we're going to have dy dx, dy du, times du dx. Those are both derivatives I can calculate. This means take the derivative of y with respect to u. That's 8u to the 7th. That's a simple power function. Times du dx. That's also easy. This is a quadratic. So 2x plus 3. Now that doesn't look right. We'd like to get a formula here that, since we started with x's, only involves x's. Right? But look, we know that u is equal to this guy. So 8 times x squared plus 3x minus 10 to the 7th times 2x plus 3. That's our final answer. We're going to come back to that in just a minute and see mechanically how we can think of this, or procedurally, to make this simpler. Okay, but that's the idea. The rate of change of y with respect to x is the product of the rates of change. Right? The product of these two rates of change. All right. How about the mechanics? All right. When we have a composite function, you might think of it as y equals the outer function applied to the inner function. Compare that to the notation we had before, which is y equals f of g of x. So g is our inner function, and f is our outer function. And so what the chain rule says is we have to differentiate the outside function while leaving the inside function alone. Right? Sometimes I call this the cover-up rule. Right? I start by covering up what's on the inside, and I worry about the derivative of what's outside. Right? And after I've done the derivative of the outside piece, right, then I put back what was inside. It hasn't been touched. But the chain rule part says we now have to multiply by the derivative of what's inside. So thinking of this in terms of outside and inside functions is often a very useful way to remember how to do the chain rule, or the procedure for the chain rule. Right, so let's look at a couple of our examples here. If we have y is equal to our composite function here's my inner function, and my outer function is this guy here, which takes something to the 8th power. Okay, so what I'm going to do is take the derivative. Here's how the chain rule works. I cover up what's on the inside, leave the inside function alone. I'm going to differentiate the outside function. The derivative of something to the 8th power is 8 times that something to the 7th. Doesn't matter what's on the inside. Leave the inside alone. And then I have to multiply by the derivative of the inside. The derivative of the inside, 2x plus 3. All right, there are plenty more examples in the upcoming video.